Hello and welcome to another presentation, this time on parametric equations, parametric differentiation, implicit differentiation and rates of change. So we're going to run through three separate ideas really here. I'm going to talk about parametric equations and the way that we differentiate them, or a possible way to differentiate them. Then I'm going to talk about implicit differentiation, which is for differentiating functions which aren't given explicitly. I'll talk about what that means in a second, and then finally we're going to look at a rates of change problem. So beginning with parametric equations, really at A level there are two things they might ask you to do with a parametric equation. They might ask you to find a Cartesian format of a parametric equation, or they might ask you to differentiate a parametric equation, a pair of parametric equations, giving your answer in terms of the parameter, whatever that may be. So let's start with asking ourselves the question of what is a parametric equation. Well, if you look here, we've got three good examples. A parametric equation is one where both the x and y coordinate, rather than being related directly to each other, they're related in terms of a third variable, which could be called t. It's often called theta if you're dealing with sines and coses. It could be called any letter you like really, but that variable we call a parameter. Now you might wonder, well, why express equations like this? And the answer is quite simple actually. You can come up with a lot more interesting curves if you actually define equations in terms of a third variable t. It's much easier to do some really nice looking curves. I've often seen, for example, the heart equation, which is an equation which will draw a little, love heart, if you like, for you on the board, well, for example, as well, there's another one called Eros equation, which draws a full-on picture, but they're always done those kinds of equations parametrically because it's much easier to do. It's a much more powerful way of graphing things. So that's the reason why parametric equations exist. But the Cartesian equation, the Cartesian format, which is the opposite of the parametric format, that's where y is expressed as directly relating to x. That format is nicer for other reasons. It's, for example, it can be easier to differentiate, although not necessarily, and it shows the direct relationship between y and x, and so in some ways it's easier to think about what the curve's actually doing. Anyway, one thing you might be asked to do is to go from the parametric to the Cartesian format. Now, the Cartesian format, it's named after René Descartes, the philosopher René Descartes. Let me just write that down for you. That's why it's called Cartesian. Anything Cartesian comes from René Descartes. He was not just a philosopher, like many of them, he was a mathematician as well. And he was the first person actually to write down, to come up with graphing equations on an xy plane. And that's why we call it the Cartesian format. Anyway, let's get on with it. Let's talk about how we'd go converting these two equations on the left here, x equals t plus 1 and y equals 2t minus 1, how we might go about converting to the Cartesian format. Well, actually, it's not too bad. It really isn't, because all we need to do is eliminate the variable, the parameter, sorry, I should say, it is a variable though, eliminate the parameter t. Now in this first question, that's dead easy to do, because you can just say, well, okay, looking at the left-hand equation, x equals t plus 1 implies that t equals x minus 1. That comes straight from there. And hence we can now plug that in the right-hand side, and we'll end up with y equals 2 times x minus 1, because t is x minus 1. Take away 1, and I'm sure you'll agree that reduces to 2x minus 3. And so we can see that curve, in inverted commas if you like, is in fact a straight line, the straight line y equals 2x minus 3. Now that is obviously a very straightforward one, but it could be the technique that you need to use, just a straightforward substitution. Unfortunately, they're not all that easy. If you take a look at the next one, the next one's pretty typical for anything involving sines and coses. We're going to use an identity to eliminate the parameter here. Rather than saying arc cos of x equals theta, ending up with y equals 2 sine arc cos x, it's just a very ugly way of expressing the answer. Now, you have eliminated the parameter though, you really have, but it's not really what the exam is asking for if you're sitting the A-level exam. What they're looking for is for you to rearrange, not the first equation can stay exactly as it is, but the second equation we can make it y over 2 equals sine theta. Now I'm going to use this identity, sine squared theta plus cos squared theta equals 1. Then I can simply plug those two expressions in terms of x and y into that identity, giving me y squared over 4 plus x squared equals 1. Now, you can actually leave your answer like that. The question, sometimes it says, could you leave your answer in the form y squared equals a function of x, or even y equals a function of x? It will choose whichever way is natural. If it doesn't choose that, it would be perfectly acceptable to leave it like this, because hopefully your students will be able to see then that this is actually, well, depending on the level of maths they've studied, this is actually an ellipse, which is very much related to the circle, because the y coordinates have just been squashed, if you like, by a factor of 2. So yeah, this is an ellipse, and there we go. Okay, I'm going to clear the screen now because I'm going to need a bit more space for the last one. Even though the last one looks very similar to part 2, this one's actually much more difficult, and that's because, and I hope you see this straight away, that's a double angle. And if that's a double angle, what we really want to do first is convert them both to single angles. And the double angle formula for sine 2 theta is that it equals 2 sine theta cos theta. Okay, now we're okay plugging the x coordinate in there. That can pop in like that. But once again, I'm going to need to use a trig identity. Now you might need to use 1 plus tan squared is sec squared sometimes, or 1 plus cot squared is cosec squared, but here sine squared plus cos squared is 1 will serve us nicely again. If we know that sine squared theta plus cos squared theta equals 1, well, bearing in mind x is cos theta, hopefully you can see with a quick rearrangement that sine of theta, missed off the theta there, is 1 minus cos squared square rooted, but that's 1 minus x squared square rooted, and now I can actually eliminate the parameter. I can say y equals 2 root 1 minus x squared times by x again, and let's put the x in. We probably wouldn't put the x in at the end because it would look a little bit ambiguous. I suppose I could put it in brackets, but to be honest with you, if I was writing that down to make it nice and clear, I'd call that y equals 2x root 1 minus x squared, just because it's less ambiguous in the way you notate it. And you do want to worry about that in the exam, because you know you don't want your work, your correct work, to be misinterpreted. And that's how we convert from parametric to Cartesian format. Most of the time, well, it's probably 50-50. Sometimes you'll use a straightforward substitution, sometimes you might need a trig identity as well. Okay, so that's nothing to do with differentiation actually, but because there's some parametric equation work in here, I thought it prudent to go over those ideas. Okay, parametric differentiation. Let's move on to the second part, and I'm going to keep this on the screen. There we go. But the key result for parametric differentiation is that dy by dx equals dy by dt divided by dx by dt. Now I hope you've started to see, if you haven't realised already, that the nice thing is about writing dy by dx, dy by dt, dx by dt, and that way of notating differentiation, as opposed to, for example, f dash of x, is that you can see that these things behave exactly the same way as fractions. The reason why dy by dx is dy by dt divided by dx by dt is because dy by dt divided by dx by dt is exactly the same as dy by dt times dt by dx, because we flip the second fraction round. The dt's cancel, leaving dy by dx. It's a really simple result to prove to the kids, and so, you know, why not show them that result. If they start treating rates of change problems and chain rule kind of like set up like that with d's and dx's and dy's, if they start recognizing that they can be treated as fractions, it will never lead you astray. It's always correct. By the way, that is Leibniz's notation. Newton, when he independently discovered calculus, he actually used f dash of x and f double dash of x. So we and also dots above letters sometimes as well. So yeah, this is really kudos to Leibniz, who developed this notation. And the notation's really nice because it's almost a subtle teacher. Okay, now obviously when you're doing parametric differentiation, you could first convert to the Cartesian format, and I'm just going to write down the Cartesian formats for these three up here. Especially for the first one, because I just want you to see straight away that you get the same answer. Now, often they'll ask you for dy by dx in these questions in terms of the parameter, which is why you definitely want to use this result. So if we're using it for the first one, all we need is dy by dt. Now if you differentiate y with respect to t there, you get 2, because 2t minus 1 differentiates to 2. dx by dt, well, that's going to differentiate, I'm sure you'll see straight away, to 1. And so dy by dx is dy by dt divided by dx by dt, which equals 2. That is particularly obvious because if I was to differentiate the Cartesian version, I would also get 2. Yeah? Now that one hasn't got the parameter left in it for dy by dx. Just because it's constant. The gradient is constant, it's always 2. It's more useful in equations like question 2 and question 3. So let's do this next. Once again, we're going to do dy by d theta. That differentiates to 2 cos theta. dx by d theta, that differentiates to minus sine theta. And so dy by dx in terms of the parameter theta is simply going to be dy over d theta, 2 cos theta, divided by dx by d theta minus sine theta. And you're done. And yes, that is the same as minus 2 cot theta if you wanted to write it like that. Okay, let's do the last one. This won't be too tricky either because it's pretty straightforward differentiating this. dx by d theta, I don't know why I'm differentiating that first this time, probably because it's on the left hand side and I'm reading from left to right, is still minus sine theta. dy by d theta, well that's 2 cos 2 theta, as the number kind of springs outside when you're differentiating a double or triple angle in sine or cos, and hence dy by dx is 2 cos 2 theta over minus sine theta. Note this time I can't actually express it as cot theta because I've got a double angle on the top and a single angle on the bottom. I would need to use double angle formulae if I wanted to turn that into anything else. But I'm fine with it as it is. But after that, of course, the question may well go on to ask you about finding tangents, normals at given values with specific parameter values. Remember, the parameter is associated with an x and a y coordinate. So you can always find tangents and normals in exactly the same way, dy by dx being the gradient of the tangent, minus dx by dy being the gradient of the normal. But that's the kind of thing they'll follow up a question like that with. Okay, so that was a quick reminder on parametric equations. Let's actually look now at implicit differentiation. So, implicit differentiation, well, it is very, very similar in that we can use a little chain rule kind of like, or a chain of d something by d something to express how we're going to do it. Essentially, implicit differentiation is for differentiating functions where they're not given explicitly. That seems pretty obvious. What does it mean by a function to be given explicitly? Well, it just means it's given as y equals. Now, not every function is given as y equals. A good example would be circles. They're normally written as something like x squared plus y minus 5 in brackets squared equals, I don't know, 36 or something like that. If that's the case, then you can use implicit differentiation to work out dy by dx. Now, both of these functions are given implicitly rather than explicitly. They're not given as y equals. And so this rule up here is very useful. Now, how can we use this rule? Well, essentially we're going to differentiate everything with respect to x, and that is what that is telling me. I'm going to differentiate things with respect to x. But if I've ever got a function of y instead, what I can do to differentiate something with respect to x is I can differentiate it normally with respect to y though, and then just times it by dy by dx. And that's exactly what I'm going to do in this first equation here. So I'm just going to write it down again, just so it's above and so it's nice and clear. I want to point out what's going to be the difficult bit here. Let's do the easiest bits first. When I'm teaching my students this, I often say let's differentiate. And remember, we're doing d by dx to everything. We're differentiating everything with respect to x. Now what does 5 differentiate to with respect to x? That's just 0. It's a number, it's a constant, it differentiates to 0. What about x squared? What does that differentiate to with respect to x? Simply minus 2x. Those are the easy bits, because they don't change at all. The trickier bits are where you've got y involved. Now this is going to be the next most difficult bit, but it's not that bad, because we simply differentiate with respect to y and then stick a dy by dx on the end, because differentiating with respect to x is exactly the same as differentiating with respect to y and then multiplying by dy by dx. It's the same process. However, the really tricky bit comes here, and I hope it's because you can see straight away that's a product, and so we need product rule as well. So what I'm going to do is I'm going to differentiate the x squared first, giving me 2x. Now did I differentiate with respect to y there? Absolutely not. I just differentiated with respect to x. So now I'm going to multiply it by the other side, undifferentiated. Plus, now I'm going to differentiate y with respect to x. Sorry, that's supposed to be a plus. Let me just go over that, make it a bit clearer. Now I'm going to differentiate y with respect to x. Now y would differentiate to 1. Now times it by dy by dx, and then multiply it by the x squared. And apologies, that looks really quite messy now. Let me just write that down clearly underneath. So we get y squared, 3y squared, sorry, dy by dx, plus 2xy, minus, plus, that's a plus, I can't read my own handwriting, it's so squished up, dy by dx, x squared, minus 2x equals 0. Now once you've done that bit, that is the tough bit, because the rest of it, to write this as dy by dx, is simple. You'll always be left with a couple of terms, 2 or 3 terms, or maybe just one, just depending on how many functions of y, terms had functions of y in them. Yeah, you'll have a couple of those. I'm going to now factorise it, so that I've got the dy by dx on its own, 3y squared plus x squared. I'm also going to move, I hope you don't mind me doing this all in one go, I'm going to add the 2x and take away the 2xy onto the right hand side of the equation. Then I can see that dy by dx is 2x minus 2xy over 3y squared plus x squared. And we're done. Okay, let's actually have a go at another one. Let's do this one next. So let me write it down up here. Ln y plus sine x squared equals 3x. Now you don't have to do it in the order the funny order I did last time. I just want to do it from easiest to hardest on the first bit. Let's just differentiate ln y straight away. Ln y would differentiate to 1 over y, and then we need to times it by dy by dx because we differentiated a function of y. Sine of x squared, well, we need a bit of chain rule here, and I'm going to do this quick chain rule. So I'm going to differentiate within the function, I get 2x. Then I'm going to multiply that by the derivative of sine of stuff, which is of course cos of the stuff. So that would differentiate to 2x cos of x squared. And that's going to equal 3. Okay, all I need to do now for this one to make that dy by dx equals is I need to move across the 2x cos x squared, so I get 3 minus 2x cos x squared, and then multiply by y, and it's done. So that's implicit differentiation. I always say to the students, it's one of the easiest bits of C4, at least on the example that I was teaching on, it was C4. It's one of the easiest bits of C4 once you get the hang of it. Although oddly enough, I remember finding it tough myself at A level, so there you go. Maybe it is quite trickier for them than I expect, but I don't remember finding that easy at A level, and I look back on it now and I think it's such a simple thing to do. Okay, next up we've got rates of change. Now, students live in a little bit of fear of these kind of questions, and I don't think they're as bad as they sound. Now, all we're going to use in a rates of change problem is the chain rule. However, it's all in the interpretation, these kind of questions. We're told that the volume of a sphere here is increasing at a rate of 100 centimeters cubed per second, and I'm always keen to say to the students, the units are really, really handy. Yeah, they're really, really useful. I'll say a bit more about that in a second. Volume of a sphere, though, let's say we're blowing up a balloon, is increasing at a rate of 100 centimeters cubed per second. So the rate is constant. We're gaining 100 centimeters cubed in volume every second. Find the rate of increase in the radius of the sphere at the instant when the radius is 3. Okay, the first thing I'm going to talk about is that first sentence. Volume of a sphere increasing at a rate. As soon as you see the word rate, you know it's d something by dt. And as we're dealing with the volume, it must be volume with respect to time. How do I know it's d something by dt? Well, it's clearly time, because we're dealing with per second. Yeah, it's the change in volume with respect to time. And look at what we're doing here. We're taking a volume, centimeters cubed, and we're dividing it by seconds. That's what centimeters cubed per second means. So it must be volume divided by time, so it's dv by dt. So we know dv by dt is 100. Yeah? We also know that we're looking for, it says find the rate of increase in the radius of the sphere. That's not find the radius, because we're told the radius is 3. We need the rate of increase of the radius. That is dr by dt. Yeah, that's what we want. So I'm going to put dr by dt equals question mark. So we've got dv by dt. We're looking for dr by dt. What's the only other thing which could be useful to us? Well, it's a sphere. So we know the volume of a sphere. Volume of a sphere is 4/3 pi r cubed. Now, on the face of it, that might not be very useful. But let's try and set up a chain rule relationship. We want dr by dt, so let's write down that. Now, dr by dt is going to equal something multiplied by something, and we need a dt in there. So, and we also obviously are going to use this bit of information, so I hope you don't mind me writing down dv by dt. Now we want that dt to remain there, but we don't want the dv anymore, so this one must have a dv on the bottom, and on the top there must be a dr, because I want it to turn into dr by dt so that they cancel, leaving dr by dt. So that's the chain rule relationship I'm going to use. Now this is no problem, I've got this. Dr by dv might seem a problem, but hang on a second. I can work out dv by dr. I just differentiate that. And if you differentiate that, you get 4 pi r squared with respect to r. That means that dr by dt, which is what I'm looking for, equals dr by dv. Now remember, according to the rules, we can just flip that and make that 1/4 pi r squared. That's a handy trick because these things behave just like fractions once again. So all we've got to do is 1/4 pi r squared and multiply that by 100. Now the last thing we haven't used yet is the fact that the radius is 3, r equals 3. Plug that in. We need to square it, then times it by 4 pi. Let's leave our answer exact. And I'm even going to put some units on because we're dealing with radius. divided by time, it's centimetres per second. That's the rate at which the radius is growing every second. Okay, I hope that presentation was useful. Best of luck to you with the rest of the course. Please do email me if you're stuck on any of the problems, and I'll do my best to help. Okay, all the best, and yeah, bye bye.